Okay, we'll continue this section on one-sided limits and continuity. In number 19, we're asked for the two-sided limit as x approaches 1 of f of x. And we have a piecewise defined function. From the left of 1, the function behaves as x cubed plus 1. From the right, from 1 and on to the right, it behaves as x plus 1. So both sides of these, or both branches of this piecewise defined function, are continuous everywhere in and of themselves. The only place that we need to be concerned is at the place where they potentially meet, and that's at x equals 1. So all we have to do for this is plug in x equals 1 from the left and x equals 1 from the right. So I say, remember, the two-sided limit as x approaches c of some function will only exist if the limit from the left exists, the limit from the right exists, and the two limits equal each other. So we know that limits exist on the left and on the right everywhere. Now, do the two limits equal each other? To find that out, all we have to do is plug in 1. So with the top, we get 2, and with the bottom, we also get 2, and so that limit is simply 2. And we would write it like that. So with these types of piecewise functions, to determine if the function is continuous as a two-sided limit, you need to make sure that both one-sided limits exist and they agree. With number 21, we have the limit as x approaches pi of cotangent of x. Well, you may not recall what the cotangent function looks like, but it's good enough to note that the cotangent of x is the cosine of x over the sine of x. And as x approaches pi, cosine of pi will be -1, and sine of pi is 0. Now in this case, we're asked for a two-sided limit, and clearly we don't have 0 over 0, or we can't plug in and get a specific real number. So because of that, we definitely have a vertical asymptote for the cotangent function whenever x is equal to pi, and in this case we're not asked for a one-sided limit, so I don't want to determine whether it's going to positive or negative infinity. All I need to say is that the limit does not exist. With two-sided limits, if there's a vertical asymptote, I simply state that it doesn't exist. If I'm asked for a one-sided limit at a vertical asymptote, then I should plug in some numbers close to the limiting value from the correct direction and see whether I'm going to positive or negative infinity. But here we'll stop it at that. And I'll go on to problem number 23. We're skipping down to problem 31. So in 31, we want to discuss the continuity of the function on the closed interval. Well, in this particular function, it happens to be a semicircle centered at the origin with radius 7, but you might not pick that up from the beginning. But it's one of the forms that you might want to begin to notice. So remember that the equation of a circle is, or I should say the equation of a circle centered at the origin with a radius of 7 is x squared plus y squared equals 49. If we were to solve that for y, or first for y squared, we'd get y squared equals 49 minus x squared. And so y would be equal to plus or minus the square root of 49 minus x squared. Now in this particular case we only have the positive, so that would just be the top part of the semicircle. Now because of that, its values only go from -7 to +7 inclusive. And so that function will be continuous for every point along that closed interval. The problem right below that is also a semicircle, but because it's a negative, it's going to be flipped upside down and shifted up 3 units, and it will be the circle centered at the origin radius 3. And we'll go on to other problems in the next video.